For students in the back, can you hear me? Okay, great, thank you. So remind me if anytime you cannot hear me. I was checking my own lecture note yesterday. Is this what you have in your lecture note? Sorry about that. It's it should be 2. But I check all our exam problem, our homework problem. There's nothing really we need in one, so we should be fine. I update in the exam review lecture note, and I update in the equation sheet I provided, so everything should be fine. Now let's get back to the example problem we didn't finish. I want to explain a little bit more. So in the last class, we were about this part. So this is the element 1 for element 1. We had the degree freedom for element 1, which is U1 V1, U3 V3, U4 V4. U1 V1, U3 V3, U4 V4, right? So the B matrix for the first element, the complete degree freedom for the first element, we get a strain component of the first element, and strain is ratio. There's no unit, so there's no unit for this term. We finished this part in the last class. Any question here? And for the same thing, the process is very similarly. It's very similar. So for the element 2, now for element 2, we have definition from node 1 to node 2 to node 3. So the complete degree freedom becomes U1 V1, U2 V2, U3 V3, right? So this is a complete degree freedom for the second element, and this is a B matrix for the second element, and B matrix times Q equal to strain. And from strain to stress, again, as I said, strain to stress, we have the C matrix for plane stress situation is depend on the Young's modulus and Poisson ratio. So this is a C matrix, and of course I provide this one in the equation sheet I posted last night. So now for the stress, as you can see that I only had one equation. I didn't really say like stress for element 1, stress for element 2. This is because if you check our calculated results, this is for strain for element 1. This is strain for element 2, and you can see that they're the same. Normal strain in the x direction, both of them, they are 0. Normal strain in the y direction equal to 0. This is a shear strain. They are the same. That's why I only had one equation, C times strain equal to stress. But of course, if somehow in some example problem you get different strain for element 1 and element 2, then you need to do this twice. So for element 1, you put the strain components for element 1 here, and you get stress components. And for element 2, you have C matrix the same, but this one, if it's different, then you need to do the calculation twice. Make sense or not? I posted this part in the announcement yesterday. So now, if you remember, in our Beam chapter, we talked about the FEA modeling accuracy. It's very important because we do want to know the modeling accuracy before we use any advanced method. So my question is that, is this result a accurate result or a just approximation? Approximation or exact? Why approximation?
Guessing.
Okay. There's any reason behind approximation? Or anyone has any other opinion?
Using a CST element to approximate it, because we're assuming that there's constant strain throughout the elements, that in itself is the approximation. And so because we're using the strain to get to stress, the stress is only an approximation.
Let me explain to her part first. I'll get back to you later. So, what you said, they are correct. So, yes, we are using CST element, and from strain to stress, we use C matrix. That's the correct. But using CST doesn't mean that it's always approximation, because I mean, what if the strain stress component they're supposed to be constant, and we are using a element that had the capability of represents constant stress strain? Then, right, from like logical way, there is a possibility that we have the capability to show the accurate results. Yeah. So the first answer is approximation or accurate. Approximation. Why?
Because
They're distributed force. I think you remember the thing in the Bean chapter, right? Yeah. So in the Bean chapter, we did this. We had this table. Yes, we had this table. So we talk about okay, if the applied force is the concentrated force or couple applied, it means that okay, from materials, we know that the deflection function should be either, if it's coupled, then it's a quadratic function. If it's concentrated force, it should be cubic function. But when we use cubic function to model this problem, it has capability to represent the exact solution. So it is exact. But when we start from uniform distributed force or higher order is linear distributed force or random distributed force, now from the mechanical materials, we know that it becomes the fourth order or fifth order. And now we are still using the cubic polynomial to model this one, then we can only do approximation. So our conclusion was, if it's concentrated force or couple, it's approximation. If it's uniform distributed or anything higher, linear distributed or random distributed force, then we know that it's approximation. Yes, you are correct based on the Bean chapter, but this is only for the Bean. This is only for the Bean. We cannot just use the conclusion from this part and you say, okay, no matter what problem we are dealing with, like plane stress, CST element, if it's distributed force, it's approximation. If the concentrated force is, we cannot really like just move the conclusion in this chapter to chapter 6. Yes. So any other opinion? Anyone? Try to, let's say if you forget about FEA, you just imagine you only learned mechanical materials for this problem. You have a square element, square structure, and you have this force applied. Purely from mechanical materials, what is the stress in this structure? Forget about FEA. Purely from mechanical materials, what is the stress?
it'll be a shear stress, but there won't be any like tensile pressure.
Correct. Yes, that's only shear stress, or other are zero. Now, of course, if we want to know if our FEA method is approximation or give accurate result, we need to know that from mechanical materials for this square element, is the shear stress constant or not constant? So we know that, let's say there are two possibilities. One is constant, and we use constant strain triangular to model it. So it means that our FEA result our FEA method give an accurate result. If from mechanical materials is not constant, it can be changed within this element, and we still use CST element to model it, it means that our FEA method gives approximation. So now my question is the only non-zero stress is shear stress. Is it constant or non-constant based on mechanical materials? Constant. How many of you agree it's constant? Okay, yes, correct. It's constant. So now we solve the problem. We cannot. So I just want to remind you guys that it's great that you know what you learned in the Bean chapter, but do not just like use conclusion from the Bean chapter in this chapter directly, because I already explained why in the Bean chapter distributed force is considered as approximation, why couple and concentrated force applied is exact result. Here we need to do the analysis separately. You cannot use just conclusion from that chapter directly. So here we know that, wait a second, when there's a, in the mechanics material, this is shear force applied on the top edge, right? I have a plane stress structure. I clamp the bottom surface and apply a force in this direction, or let's say this is positive X. And the only stress generated in this structure, shear stress. There's no normal stress in X, there's no normal stress in Y. To generate normal stress in X and Y, if from tension compression, let's say if this is X-axis, I need to apply tension compression force in this direction, right? To generate normal stress in the Y direction, I need to apply tension compression in the Y direction to have epsilon YY. Or I can apply a bending to generate normal stress, right? And if the bending moment change in the structure, let's say I apply a contrary force at this point, and the bending moment change through the whole beam, there is also shear stress caused by bending. But here, we don't have bending moment applied. We don't have the force tension compression in X direction. We don't have the force tension compression force in the Y direction. So there's no normal strain in the X and normal strain in the Y. We only have shear strain. And this shear strain from mechanics material should be the force applied on the edge divided by this area. It's constant through the structure. Make sense or not? And now, from mechanics material, we know that stress is already is a constant. And we use CST to model this problem. It is accurate results. Make sense or not? So now let's check. That's why I keep emphasizing, like, if you check this result, I said, when you do the exam problem, you can only use the FEA method. Because if you check the final result, let's say after 7 steps, this is 10 to the 5th Pascal. Let's check the force applied. From mechanics material, just by reading this problem, you know what is stressing. Make sense or not? 10 to the 5th Pascal. This is 100 kilonewton per meter square. It's the same. Makes sense. But of course, this is just help you understand, because FA is not just like math, matrix, vector operation. I just want to help you understand the physical meaning behind it. In your exam, please do not just, when you see this problem statement, and just write, okay, stress equal to, no, shear stress equal to, and you're done. No. I cannot give any points if you do it. You still need to use our FEA, because this class is training how about FEA. Of course, we try to use the simplest example problem for hand calculation, but it doesn't mean that you can just simply say, okay, this is equal to shear stress equal to 10 to 15 Pascal. So this is just help you understand what does this problem really means. But at the same time, I use this simplest example to help you go through the steps from the B matrix and C matrix, K matrix, and solve unknown degree freedom, calculate strain, calculate stress. And you know that when you put the plane stress in abacus, if something goes wrong, you know how to fix it. Because this is basically the procedure with how abacus solve your problem when there are 1,000 nodes. Right. Any question for this part? But of course, this is a simple example. As I said, when you have this structure and you only have the shear force applied, there's only one constant term, that is shear stress. And the same thing, let's say I also have a plane stress situation, I clamped at the bottom and apply a force on top. And it's still okay to, CST limit still can give you accurate result, because in this situation, there's only one constant stress in our structure. Makes sense or not? Epsilon YY, sigma YY. Strain stress, non-zero term. Normal strain, normal stress in the Y direction, all other zero. So in this situation, of course, if we use a CST element, it can still give you accurate result. It's not approximation. But of course, these are the simple situation. What if we have a situation like this? So this is a plane stress problem, but it's the force applied is force here in the positive x and the force here in the negative x. And since the distance between it form a couple. And this is more like a beam bending problem. And for this one, let's say if we use the CST element to model this situation, do we have approximation or accurate results? Approximation 1. How does the stress change across from mechanical materials? How should the stress change?
More stress towards the end.
You mean more stress here?
Stress towards the other.
This end? Which end?
I believe towards the end, but
Okay, more stress towards this end. Why? More bending moment towards this end? Why? Bending moment is constant. Bending moment is constant. So there's a, again, when you have a couple, we know that it's a couple applied, right? When you apply couple here, the bending moment in this beam is constant. The one, let's say if I apply a force like this, then the bending moment is not constant. The bending moment is equal to magnitude equal to, sorry, F times distance. And then you can say that if I apply force in this direction or upward direction, of course, and then bending moment is the magnitude is maximum at the root and minimum here because the distance is an interchange increase, right? But when we have a couple applied, the bending moment is constant, right? So now we are clear about the bending moment, how the bending moment changes in this structure. How does the stress should change? Yes. How does it change through in the y direction? Linear change. Do you remember any equation related to that linear change? Yes, thank you. Thank you. So in the mechanics material, we have a whole chapter using this equation over and over and over again. So I hope you guys still remember this one. So beam bending, how to calculate the stress generated by normal stress generated by beam bending, we have my of I. And of course, we normally define this is the x-axis and this is the y-axis, and x-axis normally we put out the neutral surface of the beam. So since bending moment in this one is constant, moment inertia, of course, is constant if the cross-section is constant through the beam. So the stress sigma xx is linear change with y. So here, basically, if you want to plot how the stress actually change of the cross-section, it should be linear change. And this is the neutral surface. Normal stress equal to 0. On top of the surface is maximum, but it's compressive stress. At the bottom surface is maximum magnitude and it's tensile. Makes sense or not? Because let's say it's bending in this way. So this is how the stress should change in the structure. But now if we use CST element, means constant strain or strain and stress that in the same order. So constant strain or constant stress element to model our problem, it can only give approximation. Make sense or not? So now you can, I think in one of tutorial 4 or 5, tutorial 4, I showed this one in the tutorial 4. Let's say first we try to use 10 elements. And now you can see that these are different color. And of course, you probably already know that this is stress plot. In Abacus or ANSYS any FEA software, the color represents the stress level. So normally when you go to the red color, it means a higher stress. And when you go to the blue color, it means lower stress. So now you can see that it should really change, but you can see in this whole CS element is the same stress, same stress. Of course, there's some jump from higher stress to lower stress because I already explained that the upper surface is compressive, bottom surface is tensile. So there's some jump, but within each element, they are constant, right? And we know that this is approximation. And you can see here, this is the maximum stress when we use 10 elements. And when we know that it's approximation, we want to use more elements. And this is what if we use 20 elements. What if we use 20 elements? And then you can see that, okay, again, within each element is still same color, means constant stress, right? And this jump from here to here to here to here. And now you can compare the maximum stress from here to here. When we increase number of elements, the stress increased. And of course, in FEA, you can do a convergence study. Let's say you have X is number of elements, and y-axis is stress. Let's say this is a sigma xx from bending. And then you have 10 elements, you have a stress result. You have 20 elements, you have another stress result. And you can keep plotting. And when you see when you gradually converge, you know that you can stop, right? And of course, it depends on like the accuracy requirement and also the computation time you can afford.
Would it be best just to make really short, long triangles that go the entire length of the beam, since all the triangles are going to be equal at the top and on the bottom, to like stack them vertically rather than horizontally? Just trying to get stress.
You mean this is one triangle and this is one triangle? Is that what you mean?
Yeah, but then stack more of them, but that go the entire beam.
Yeah, you can do that.
So would that be better to get the stress?
So you are talking about, let's say you have triangular element like this, and more triangular element and more triangular element. So this is more of advanced topic. In the CST element, well, the best result is that when you have the equilateral triangular element. So if the interior angle, each angle is close to 60 degrees, you get the best results. And when you have, let's say if you have something like this angle is very small and it's more like distorted CST element, and it's more away from 60 degrees, less accurate it is. So we always want to avoid that the interior angle is too small or too large. So mathematically, we'll talk about this later. If we have time, mathematically, we want the angle between 0 to 180, mathematically, to make it, we're able to calculate everything like inverse and everything, Jacobian. But abacus, when you do the plane stress, you can check later, that do not allow you to have any interior angle that is lower than 15 degrees or higher than 165. And also, let's say if you have complicated structure, they allow you to do the partition. So let's say some of you may seen a torque arm design like this, and then there's a hole here, and it's complicated geometry. And if you do match, they may have like really weird triangular element or quadrilateral element, and some angle they are really distorted. The elements they are really distorted and they cannot give you good results. So they allow you to do the partition. So you have like a regular shape each region, and then do the mesh within each region to make sure that the angle is not the CST element or the quadrilateral element, they're not distorted too much. So for the CST element or the triangular element, we want to have the interior angle as closer to 60 degrees as possible. For the quadrilateral element, we want the interior angle to be closer to 90 degrees as possible. You don't want to like distort it too much. Otherwise, there's no point to do FEA. It will not give you accurate result anyway. Thank you for the question. Any other question? Okay, so this is we're done for the CST. So basically, we're done with this interpolation, and strain and stress, K matrix, work equivalent node of words, and modeling accuracy. So this is the same for the beam chapter. Beam chapter, we also talk about interpolation, bending moment shear force, K matrix, equivalent node of words, modeling accuracy. And you can see now that if you put everything together, it's just like repeating the same thing for each type of element, right? And again, I just really want you guys to really understand from basics. Do not try to don't get confused of the content from each topic, from each chapter. Is there any other specific question you guys want to ask for this exam review? I want to answer your question first before. So we likely have 4 calculation problems. They'll be similar as our example problem in the class or homework problems. And the content we start from the beam interpolation because we didn't really include beam interpolation in the exam 1. So we start from here. And shape function as that distribute to. This is the 4 shape function and for displacement in X and displacement in Y. Oh, sorry. That's the CST. Sorry. This is the interpolation for deflection and rotation. You just take one derivative. So N1, V1, N2, theta 1, N3, V2, N4, theta 2. And these are 4 shape function. Example problem we did in class. Of course, VS is direct application of this one. You plug in the V1, theta 1, V2, theta 2, right? And this one, rotation, is the derivation of the deflection. Don't forget the Jacobian because the definition of the rotation equal to dv over dx. But here is everything is written in terms of the reference coordinate, so it's dv over ds. So what you need to do is that dv over ds over dx. So there's 1 over L Jacobian after this operation. For deflection and slope at any specific point in the physical coordinate, you need to find the corresponding s in the reference coordinate and then plug back in. So 1.5, and if the total length is 2 meters, then it means that s equal to 0.75. So this was example problem, and our homework problem very similar, very similar. Again, all degree freedom are given. All degree freedom given. It's just this example problem we have numbers, and this one I have put as force, length, Young's modulus, and moment inertia. Question the same thing, and this is middle point, and we know that middle point means s equal to 0.5. So same problem. And we also talk about K matrix. And I mentioned 2 methods for calculating shear force and bending moment. This is based on the sign convention. Check reduction notes. The sign convention. So we can use this one to calculate shear force and bending moment at node. This method cannot calculate like within the element, but it's at node. The second method is based on the definition of bending moment and shear force, and this one you can plug in s equal to any random value, and you can calculate bending moment and shear force at any random point within the beam. So these are 2 different methods for calculating bending moment shear force, and of course we didn't go like one step further because you probably realize that in the bar, in the truss problem, in the CST element, we always talk about calculating stress. We can go one step further, like once we have the bending moment shear force, how to calculate stress. Then it's basically for the normal stress called generated by bending is my negative my of I, and for the shear stress caused by bending, if the bending moment change or non-zero, then the shear stress equal to VQIT, which becomes a problem from mechanics materials. We can always go one step further, but here we focus on FEA here. This is an example problem we did in class. So we have the boundary condition, we have the force applied, we have the material property and dimensions. Solve for unknown degree of freedom, KQ equal to F. Make sure that the KQ equal to F for solving the unknown degree of freedom should all be done for the whole system. You cannot just take one element and its KQ equal to F and solve for unknowns. No, this is a complete system. So you need to have the K for this one, K for this one, do assembly, apply boundary condition. And again, I suggest you guys always try to ignore the part that relates to boundary condition here. So you can save some time. Do not always write 4x4, 4x4, and 6x6. You probably will not have enough time for your exam. And calculating bending moment and shear force, you can use either method here. So this was the example problem in class. And the homework problem is a little bit different because normally we have KQ equal to F. Here Q is given. So KQ equal to F, K and Q are given. You need to calculate F. So it's the same equation calculated in different direction. These are all the unknown degree of freedom. So element 1, element 2, you have the K for element 1, element 2, and all the degree of freedom deflection for each node, they are fixed because we have the pin joint, vertical support, and roll support. So based on this one, you can calculate the couple applied at each node. So for the reaction support, you can go back to the element since it's asking about node 1. You can go back to the element matrix equation. You have the K for the first element, and you have all the node degree of freedom. So you can calculate reaction force. I can show you the solution here. K for element 1, K for element 2. Do assembly. This information is given. You need to calculate this one. For calculating reaction force, now it becomes for element since asking about node 1. So K for element 1, Q for element 1, and this is something asked about. You don't need to write the first 3 rows because they only ask about F1. Again, no need to write the complete matrix. This was one of the homework that confused you guys a lot. But I think the main problem is come up with this linear equation, the Q as a function of S. So again, the Q naught given here is the magnitude at this end. You cannot just write QS equal to Q naught. No. So here, pure math. If we know that it's linear distributed, so there should be constant term, there should be linear term. And we know that at the left side, when S equal to 0, it should be equal to 0. At right side, when S equal to 1, it should be negative. There's a direction here, negative Q naught. So 2 equation, 2 unknowns, solve for the 2 unknowns, we get a straight line. And of course, this is a standard procedure, how we come up with a straight line. We have 2 points, we know how to identify this straight line. And I can easily change this one to here, or it does not need to really start from 0. I can have a random straight line like this, or random straight line like this. It should be the same, right? This is a standard procedure. 2 data points can identify a straight line. So it doesn't matter what the linear force should look like. It does not need to start from 0, and it can be in any shape. So once we have this Q as a function of S, then becomes integration of the QS. If we use shape function N1, it becomes F1. When we use shape function N2, C1, shape function N3, F2, shape function N4, C2. I guess we use this one here, but it's okay. I will talk to the TA. If somehow you guys use the 3, we'll not give you any penalty. So this is finding the equivalent of the force. Any question for this example, for this homework problem?
So I guess that's Q zero because of what's going down.
Yes.
Okay.
The negative sign period because of downward. Yeah. Any other question? So this is for work equivalent force, and of course, the example we did in class is much simpler. We assume that what if the PS equal to P, uniform distributed force, and of course, this one you can use in your exam directly. I already provide this one in the equation sheet. So this was the example problem. This was a homework problem. And combine everything together, we have more of real life problem. We have the boundary condition. What do you mean by opposite direction? Like this?
Yeah.
Let me put it here. Still going down, going up? Direction. The direction is going up or going down? Going down. What do you guys think? What should be the function? Yeah. So the method, if you're not sure, you do not need like, oh, you look at this straight line, you get the function. You can still go through the standard procedure, right? So let's say we always, for straight line, Q as function S, we should have a constant term. We should have a linear term for straight line, right? And we know that at S equal to 0, which represent this end, right? And let's say this point equal to negative Q naught, right? So when S equal to 0, Q S equal to 0 should be equal to A naught, should be equal to negative Q naught, right? And at this end, S equal to 1 is equal to 0, QS equal to 0. So S equal to 1, Q1 equal to A. Let's write directly. Wait. Plus A1 equal to 0, right? So A1 equal to negative positive. Makes sense or not? And now, of course, QS equal to A1 is Q naught minus Q naught S. Okay, great. But of course, you can always double check. Let's say when S equal to 0, negative Q naught. Oh, sorry, I wrote it wrong. Should be negative. When S equal to 0 is negative Q naught here. When S equal to 1, equal to 0, right? So it doesn't really matter. And also, as I said, it does not really like one end should be 0. It can be any straight line or like this, right? It doesn't really matter. Any other question? Okay, so now we combine all the topics in the in the bin element into one problem. Then you need to solve the problem. So first, you need to come up with the KQTF, solve unknown degree of freedom, and then you need to calculate, use the interpolation with the nodal degree of freedom. You need to calculate deflection, rotation, right? Or we may go one more step, calculate bending moment shear force. So here the same thing. Give the structure boundary condition or loading condition, you need to calculate the nodal degree of freedom, unknown degree of freedom, and calculate bending moment shear force. So it's more like combining all the topics in one problem. This was example problem, homework problem. It's the same thing. I can change the loading condition in any way I want. I can change the boundary condition in any way I want. But if you know how to stand this type of problem, it doesn't matter, right? You can put these three problems together and you can understand the whole thing much better. And now for the CST element, we spent a lot of time just now talking about CST element. This is the f and b and c and shape function 1/2a f and b and c. And of course, all these are provided in the equation sheet. So this is for displacement x, displacement in y. And if it's a point on the edge, 1D interpolation can simplify your calculation a lot. You do not need to go through all these procedures if it's a point on the edge. I had one example show you how to use 1D interpolation, try to check the action node. And once we have the node degree of freedom, we already have all the F, B, and C. Of course, we know the B matrix. We can calculate the strain. And of course, I already showed it in the example problem that if we already have the function of U and V as a function of X and Y, we can use the definition to calculate the strain components directly, if that is simpler, of course. And from strain to stress, this is C matrix. Example problem in class, we gave all degree of freedom, we gave all the coordinates, displacement. I asked two because this is the point in the element, this is a point on the edge. Try to understand both. Homework, same thing. All the coordinates, all the degree of freedom. So this one and this one, they are the same problem. I can change the coordinates in any way I want. I can change the displacement in anyone. They're the same problem. And calculate strain components. And U and V. So one more step. It's not just the displacement, but also the strain components. For the different metric for the CST element, it's HA B transpose times C times B. So I will figure out how to test you guys in the exam. So this is more like the work equivalent of force. Mathematically, you do need to do the integration of the shape function times PS to get the equivalent of force. But I explained in the class, since we only try to deal with the simple situation, which is uniform distributed force applied on the edge or uniform distributed force of the volume. So the easy way to understand that there's no reason why one node to get higher equivalent of force than the other. So if it's applied on one edge, let's use edge 1, 2 for example, then divide by half. Goes to node 1, node 2. And in the y direction, half 1, 2. If it's over the volume, divide by 3, go to 3 nodes. Same thing for y. So actually, the work equivalent node force, they are simpler than the Beam chapter. This was the example problem we did in class. This was the homework problem. So this one, they're the same. Right? They're the same. This one is a little easier because I give it the K matrix directly. So here, the K matrix seems huge, but you need to know that since this whole edge is come to the wall, so everything related to node 1 and node 3, they are gone. So let's say 1, 1, 3, 3. You only need this 2 by 2. Right. So actually now you can see that this 2 is actually very easy. There are 2 0 components here and just 1. So the calculation is not complicated. You have the KQ to F and you can solve everything else. So KQ to equal to F, solve unknown degree of freedom, which is U2 and V2. And U1, V1 equal to 0, U3, V3 equal to 0, you can do the interpolation. Once you have interpolation, you can calculate strain. And of course, I can always ask one more step, calculate stress. This is exactly the same. I can show you. Oh, this is the second homework problem. KQ to F, solve U2 and V2, interpolation and calculate strain. But of course, as I said, if the previous step already have the U as function X and Y, V as function X, Y, you can use the definition of strain component directly. So normal strain in the X direction is partial U over partial X. So this should be the epsilon XX. Same thing. Definition of the normal strain in the Y direction equal to partial V over partial Y, 0, 0. And the third one is partial U over partial Y plus partial V. Let me write here. So the third one is And you can see that for the U expression, there's really no Y and V is 0. So 0 plus 0 equal to 0. So whichever that is convenient for you, you can use either method. I personally believe that you can use definition is much faster. The last homework problem. We have 3 minutes. B and C. And B matrix, C matrix, B transpose times C times B, F vector. And of course, I got this from the solution manual. So 1 to 2 to 3, of course, everything related to 1 and 3, they are gone. So we only need these 2x2 components for our calculation. And we solve for the unknown degree of freedom, U2 and V2. And for the string components, U1, V1, U2, V2, U3, V3. Sorry, I didn't make this solution. It's not my fault. So yeah, this is a string components. This is a C matrix. We get stress.
But for finite gravity, the negative, could we make it negative?
We normally consider gravity in the downward direction, and we normally consider the y-axis in the upward direction. So when it's gravity, we add the negative sign. Yeah, negative. Yeah. This negative here. Any other question? Okay. Thank you for coming, and have a great weekend.
Good question.